about an interesting second order circuit. And this is now a case using an op-amp and now using 2 capacitors and 2 resistors. Nominally, you can imagine at these values, but of course the techniques would be sort of similar in a number of ways. And so what you look at this structure, you say, well, how do I solve it? And at first it's pretty straightforward because you go, well, I see an inverting amplifier, so I take the resistance or the overall resistance, where I call it impedance, which these two are in series, go in the denominator, and these two turn out to be in the numerator for a typical inverting amplifier. So of course I have a minus sign, and we build from there. So you think, okay, that's actually not too bad. Now it does require a little bit of algebra, and the algebra steps are kind of useful because you can kind of expand this out into this term. You multiply it through by SRC, and when you look at this term, you think, okay, I need to now make some sense of what are my pieces. I definitely can see some time constants here. I also see a mixed term of R2 and C1. And R1 and C1 is a time constant, so that probably gives me an idea of how to kind of massage this and change this in such a way that I can actually get a pretty reasonable form. And so by defining this is tau 1 and this is tau 2, I can actually get this formulation for my transfer function. And you're like, okay, that's great. And you look at it closely by looking at it, I've actually got a gain term filter related to this case in terms of the R1, C1 terms, which is this creating the high pass part of it. Then I've got a 1 over 1 plus S tau 2, which then gives me this part, which gives me the low pass part of this term. So I get this sort of combination of two things. And so even if I plug in the numbers, knowing that R1, C1 is a little bigger than R2, C2, it allows me to then say I've got two separated poles, and I should actually have a pretty straightforward approach. Now I also know my gain is 10, and in fact I get very close to 10, and I get two roll-offs here and here. So this is actually taking this frequency response and plotting it in MATLAB. And you can kind of compute this out and kind of look at the result. And this is the frequency response, two very nice parts of the very nice balanced bandpass filter structure. What I also see is, of course, a fairly explanatory phase response starting about minus 90 degrees and then going through down to minus 270, with, of course, the center frequency being right at 180 degrees. And so all of this fits fairly well. It's an interesting thing because it's a second order system. All the roots are real, so it does mean I've got something with separated poles.